Welcome to the video on solving radical equations. You may have solved some of these in class already, but they were really more of the simpler kind, and in this video we're going to focus on some of the more complicated problems. And we're also going to split this up into lessons, things that we want to remember when solving, because they can be pretty different and there's some special things that can happen. So our first lesson is to isolate the radical if possible. So for our first example, notice we have a square root and there's stuff inside of it and there's stuff on the outside of it. Our job is to think of that square root as just a square root that we want to get on one side of the equation. I don't care what's inside of it. So some people like to think of this as just another variable like u. And if I rewrote that equation as 4u minus 2 equals 6, you'd say, oh, okay, I know what to do first. I would add 2 to both sides, and then I would divide by 4, and then the u would be all by itself. Let's do the same thing, but with the radical. Let's add 2 to both sides, divide both sides by 4, and now I have the square root of 3x minus 2 equals 2. Once that radical has been isolated, now I can think about what I would do to cancel out the root. So in this case, squaring would cancel out a square root. So I'm going to square both sides. And now just the radicand is left, so 3x minus 2 equals 4. And now solving for x, we would add 2 to both sides and divide by 3. So we get an answer of x equals 2. Let's move on to some more examples. For the next lesson, I'm actually going to write it down after we go through the problem. You're going to see why. Here's our next example. So let's use our lesson number 1 idea to isolate the radical. So let's move that 5 over to the other side. And now because it's by itself, right, we would square both sides of the equation. So now there's no more radical. But notice that this time we have a quadratic equation. So we started out with a square root and a linear part of the equation, right, in the beginning. And now that's turned into a quadratic, and that's going to be what's special about this problem. And now I have to solve a quadratic equation, so I'm going to try to get everything on one side, set it equal to 0, and solve that however I deem possible. And in this case, I believe this is factorable. Yep. So that factors into x minus 7 and x minus 4. If it wasn't factorable, I could always use the quadratic formula. So we have an x equals 7 and an x equals 4. But don't circle those yet, because here's where the lesson comes in. If I were to graph the left side of the original equation, right, so this is the square root, x minus 3 moves that graph 3 to the right and the plus 5 up 5. And there's our square root shape. And now I graph y equals x. You'll notice that these graphs are only going to intersect at one place. And let's count that out. That is at 7. So 7 is a correct answer. 4, we can actually see right here, they do not have the same value. And because of that, we're going to say that 4 is an extraneous solution. I just wrote an abbreviation here. EXT for extraneous, SOL for solution. And that's what our lesson is. What happens is when you increase the degree of an equation while you're solving, right? So we went from a linear to a quadratic. We created extraneous solutions. And it doesn't always happen when you increase that degree, but it often happens, especially when we're doing these square root or radical equations. And we'll see more of those as we go on. But moving on, our third lesson is that we want to avoid squaring binomials when possible. Not because we don't know how to, but because it's annoying. And simultaneously, we're going to do another lesson. Sometimes we are given radicals, right, that are have different indices, and we can raise the equation to an exponent that would cancel all of the different indices. So here's our example of a square root minus a fourth root. Right, so it says avoid squaring binomials when possible. And we also like to isolate radicals. So why don't we move one of these radicals to the other side? Now I don't have a binomial, and each of those radicals has been isolated to a different side. And now the second part of this is to figure out, well, what exponent would cancel out an exponent of 1/2 and an exponent of 1 to the 4th? Well, we're not going to cancel the exponents completely, but we could avoid some fractions if we raise everything to the 4th power, because then this exponent over here will become 1, and this one will become 2, which I can work with. And now we went from a radical equation into a quadratic equation, so you bet we're going to have to check those solutions to see if any of them are extraneous. So we do have to still square a binomial, right? That's not something I'm going to avoid here. So I squared the left side. It's a quadratic. Let's get everything set over to the left. Make it 0 on the right. And think about factoring this one. It actually does factor. And we set each of those factors equal to 0. So I get 3/4 and -1 as possible solutions. Now, sometimes making the graph is not an easy way to check things. It's much easier to plug in, and that's what we're going to do right now. So when we do a check, we're going to take that first value, so 3/4, and we're going to plug it into the original equation wherever we see an x. So that's what I did right here. And the question is, does this, right, it's not definitely equal, does it equal 0? And remember, do not start solving things when you're checking. Solving meaning like you're putting in additional operations. Nope, I'm not going to square anything. I'm not going to raise anything to the 4th power. I'm just going to follow PEMDAS rules. So the PEMDAS rules say parentheses. I'm going to do the stuff inside the square root. That's a grouping symbol. Now I'm going to try to simplify this. So 25/4 is really 5/2 squared. And now I can work with these exponents here, right? That's really a 1/2. And these things match, which means I can subtract them and I get 0. So the first check is working out. Both sides get us 0. So x equals 3/4 is a solution. Let's check -1. So if we plug -1 into both sides of the equation, does this result in 0? Well, the square root of -1 minus the 4th root of 1. Non-real and real. Not going to cancel each other out. There's no way that this is 0. So we have another extraneous solution. Moving on to lesson 5, which we will write in momentarily. Here's our example. I have a quadratic inside my square root this time. And we're going to use all of those lessons we've learned previously. We want to isolate that radical. So I'm going to move the x and the -3 over to the other side. And I know I said avoid squaring a binomial when possible, but I would much rather square 3 minus x than something with the radical. So we'll square both sides there. So inside we get this radicand. Over here we have to square the binomial. Don't forget that middle portion of -6x. And we have another quadratic. Surprise, surprise. I believe we have another one that's factorable. And there are its factors. And we have 2 solutions, right? -8 and 2 to test out. And if I plug in to do the check, I know I'm going through this fast, right? But you can always pause or try these on your own. It turns out that I do get 0. So our first answer looks good. Let's do our second check, plugging in 2 wherever we see an x. Simplifying, we get 1 minus 1, that's 0. Both things work, right? So the lesson to be learned here is that when you get multiple answers, there doesn't have to be an extraneous solution, right? Just because you change the degree doesn't mean you have to have one. Sometimes all of those solutions are actual solutions. All right, we got one more to talk about. All right, lots of radicals here. You can't isolate all of the radicals, right? Here, this one's isolated. There's no way I'm going to isolate both of these. We're going to have to square this binomial. So if we square both sides, I suggest that you write out this complicated binomial multiplied by itself. So that way you can see all the things that have to get multiplied. So when you multiply, the first's going to get multiplied. Okay, they match, so we get 2x plus 9. Moving on to the outsides, those do not match, so we're going to have a radical times a radical. Next would be the insides. Now notice that those are the same radicals, right? So these two terms are actually going to match, so we'll be able to combine those. And then the last, we're going to get positive, right? Those are both negative, so they multiply to a positive, whatever the inside was. So x plus 1, and that whole thing equals x plus 4. Okay, lots of things. We got to combine our like terms. So 2x and x, 9 and 1, that makes 3x plus 10. These two radicals are exactly the same. They are both negative, so we have negative 2 of those things, and that equals x plus 4. Still gather our like terms together. Let's bring this x over here, this 4 over here. That gets us 2x. And then we might as well bring this radical to the other side. We can start to isolate that one. Now I'm going to divide both sides by 2. I want to get rid of that 2 there. And then this is going to simplify to x plus 3. And I have a radical that I can now square. And that means that the lesson is sometimes you need to raise an equation to a power more than once. So here we go. I'm going to square that first binomial. The root's going to cancel. I now have to multiply the insides there to get 2x squared plus 11x plus 9. Still have this quadratic. Let's get that equal to 0. And now that's factorable, so we get x equals 0 and x equals negative 5. And we got to do our checks, so if I plug in 0 to the original, looks like everything works out. If I plug in negative 5, the square root of negative 1, take away something, does not equal itself, so that is not equal. We have an extraneous solution there. And if you take a look back, that's a lot of work, right? So that's what happens when you have tons of radicals that you can't combine at the beginning. You're going to have to go through a problem where you're squaring or raising to the third power, multiple times. All right, we'll do some more difficult problems in class. See you then.